Thanks.
Okay, so I will be talking about phase determination in macromolecular crystallography with Phenix. And so I knew I'm the last person talking today, and it's a dense workshop. You heard a lot of talks, a lot of theory. So on purpose, I keep this very, let's say, a little bit easier. It's an overview. I show maybe one formula, and otherwise it's more about the concepts. So here's a short outline. Okay, so first I will tell you what is Phenix, and then I will give you two reminders. One is about the phase problem. I know you heard it a lot, but I think this is a phase retrieval workshop. So the one thing you should take from this workshop is the phase problem. And then a second reminder about phasing methods in macromolecular crystallography. And then I will walk you through a tutorial, which is a brand new. It's not yet available in Phenix, but it will be very soon. It's about using an AlphaFold model for molecular replacement. So let's start. What is Phenix? Phenix is a software, and it's a collaboration between different groups. One is in Lawrence Berkeley Laboratory, that's where I'm working. And the other four groups are in Los Alamos and the New Mexico Consortium, UT Health in Texas, Duke University, and then we have the University of Cambridge in the UK. So you see that there are a lot of people contributing to that software. And so what is Phenix exactly? So it's a software for automated structure solution in macromolecular crystallography. So it's typically used for solving protein structures or RNA, DNA structures, not for small molecules or other compounds. And so the idea of Phenix is that it combines both modern programming concepts and new algorithm development. And it's designed to be used by beginners and experts. So it's easy to use if you don't know so much, but you have a lot of freedom, a lot of parameters to play with if you know what you're doing. And so we'll focus also on long-term development and support. Phenix is now, I think, more than 20 years around, or about 20 years. And why is it called Phenix? So here it's an acronym, and here you can see what it stands for. For example, the P stands for Python. So 20 years ago, Paul Adams and his co-workers, when they started developing Phenix, they thought it would be a good idea to use Python. And it was a very lucky decision, because now it's used in many contexts. So let's look at the steps that we use in protein or in macromolecular crystallography to solve a structure. So starting from the point where we have measured intensities or structure factor amplitudes, these are the steps that we typically follow. So you can see that quite a lot of steps involved, from the fact that we have the data and we can deposit a structure. So the model has been determined. And so for each of these steps, Phenix has at least one tool. It's not important that you remind all of these. I just want to advertise here that Phenix can be used for all of these steps in the structure solution process. And so this workshop is about phasing. So here I made a circle about the steps for phasing. That's experimental phasing or molecular replacement in macromolecular crystallography. So let's remind ourselves again, why do we need this step, which is very, very important. And to do that, let's go one step back. So the goal of the crystallographic experiment is typically to determine the structure. That means we want to know where are the atoms in space. And to do this, we do a diffraction experiment. So we shoot X-rays onto our crystalline sample, and then we measure the diffracted intensities. And so there is a relationship between the electron density in the unit cell to the amplitude and phase of the scattered X-rays. So this is represented by this formula here. We have the electron density, which is the Fourier transform of the structure factor. So if we know the density, so here, for example, you have a figure of the density. So in protein crystallography, we typically work with molecular viewers, and they represent the density as these isosurfaces. And you can change the contours, and you can this way see where you have density peaks. And if we know the density, the atoms are located where we have density peaks, right? So here, for example, we have this nicely shaped density peaks. And maybe for those who are biologists or biochemists, can you recognize what kind of amino acid could fit into that density? So we have, the Zoom has this chat function. Can you maybe type your guess in the chat function? What kind of amino acid would fit here? Any one of the participants? Okay, we have already an answer. Okay, and we have a few already. We have tyrosine. Most of you suggest tyrosine, and then benzene, right? So we know this is a protein, so we maybe expect here tyrosine, but it could be also some ligand that has a benzene ring. So both answers are basically correct here. So if we know where the density is, we can place a model, right? Such as this one. And that's why in the crystallographic experiment, the end goal is kind of, we want to get the density. But the problem is that we only measure structure factor amplitudes, and we do not measure the phase. And so this is the phase problem. So that means basically we cannot calculate the density. That means we cannot determine the structure. And so we need to recover the phases in order to be able to calculate the electron density. And so in macromolecular crystallography, there are several ways to recover the phases, and we can basically make two categories. One is experimental methods, and they exploit the properties of a few special atoms. So let's remember, when we work with macromolecules, there are thousands of atoms. And here we are interested in the properties of a few. That can be 5 or 6, a dozen or 2 dozen, depending on your certain cases. And we exploit certain properties that can be either anomalous scattering or a large number of electrons, or it can be a combination of both. And the other way of recover phases is based on computations. And that's one, molecular replacement. And the idea is that a previously known structure can provide initial phase estimates for a new structure. And another method is called direct methods. So there are some phase relationships that you can formulate. We saw that in the lecture from George Phillips yesterday. And unfortunately, this only works at very high resolution or for a limited number of atoms. So it's not applied very often for proteins. So let's look a little bit at the experimental phasing methods. So again, these, I should also mention, when I say here computationally, of course, we also use computational tools when we do experimental phasing. But the idea here is that we do some additional experiment. So let's look at the experimental phasing methods. So we use either anomalous scattering or a large number of electrons. These are the two properties we want to exploit. And then we have a variety of options. So this is kind of a complete list of what you can do. If you use electron-rich atoms, you can either have one or several species, so you have SEER or MEER. Then you can use a few anomalous scatterers and collect at one wavelength. That's called SAD, or at several wavelengths. That's called MAD. A special case of SAD is called native SAD. So you only use native sulfurs that are present in your sample. And then you have combinations of electron-rich atoms and anomalous scattering. That's called SEERers, MEERers. And then you have a very funny method that's called RIP. That's radiation damage induced phasing. And that's, again, a special case of single isomorphous replacement, where you use the fact that the sample is damaged with the X-rays to get some phases. So I was interested in, well, how many times are these methods actually used? These are a lot of methods, right? 1, 2, 3, 4, 8 methods at least. So I went to the PDB. The PDB is the Protein Data Bank. So it's a repository for macromolecular structures. That's really a great thing that makes it available, makes the results from one group available to the entire world. So this Protein Data Bank has now, I think that is a screenshot from yesterday, so it has more than 183,000 structures in the repository. These structures are from crystallography, cryo-EM, NMR, and a couple of other techniques. And so I was interested, how many times was a structure solved by SAD, MAD, and so on. And I got this histogram. So from among the experimental phasing methods, SAD is the one which is mostly used, about 10,000 structures, followed by MAD, about 6,000 structures. Then here we have MIR, 1,500, and then the other methods have less than 1,000 entries in the PDB. And then these radiation damage induced phasing is used probably only to show that it's possible to do. So I want to give one word of caution with these numbers. This relies on how well the depositors have actually filled in that information in the field that can be searched for in the PDB. And sometimes it's not, either people did not put anything, or they put several methods, or they put something that is ambiguous, or they have some spelling errors in it. So these numbers should not be taken really literally, but it gives trends, right? So SAD and MAD are the most used, and all the other methods follow behind that. But let's see how that fits in the general context, because phasing, experimental phasing, is just one of the possibilities. So here in this plot, you can see a bit better how the distribution is for all the structures. So most structures are actually solved by molecular replacement, almost 90%. And then we have about 9% for SAD, MAD, and everything else is about 1%. And you can see direct methods even a bit less. So the bottom line here is molecular replacement is the method of choice, and followed by the experimental method, the phasing method that uses the anomalous scattering. So let's remind ourselves a bit what was molecular replacement. So the idea is that we use a previously known structure to get phase estimates. So here you can see schematic representation of a crystal. So you have here the unit cell. In the unit cell, you have two proteins. You have one protein, but in different orientations. And so you have, for example, here two domains. They're a bit linked by this loop. And now you have a search model that looks very similar. And in the search model, you have to find the correct rotation and position in the unit cell in order to be able to use the phases of this search model to get the phases of your target structure. Now, maybe you heard the buzz about AlphaFold. So I remember yesterday there were already some questions about phasing and AlphaFold, and what does it mean? Does it have any implications? So let's just remember, what is AlphaFold? So last year, AI scientists from the Google company DeepMind, they won a competition called CASP14. That's the Critical Assessment of Structural Prediction competition. So it's a competition where people start with sequences and they try to predict the structure. And so these AlphaFold models were incredibly good. So the idea is we start from the amino acid sequence and have a structure model. And the average RMSD of these was about 1.6 angstrom. And so just if you're interested, the code is actually available on GitHub now and can be run on Google Colab. So here are some links. I will make this presentation available so you don't have to write these down. And here's a very short summary of how that approximately works. So we're starting with an amino acid sequence, and the first step is to do some multiple sequence alignment. And the idea is to find parts of the sequence that are more likely to mutate and correlations between them. If possible, we find proteins that may have a similar structure. These are called templates. And then we guess which amino acids are likely to be in contact with each other. So we can already imagine, if we know which amino acids are likely to be in contact, that will tell us a little bit more about how the protein chain will fold. So this next step uses a neural network, and this identifies which parts of that sequence alignment are more informative. And this goes to a second neural network, and that is used to build a model. So at the end, we get a structure model. And now the idea is for molecular replacement, instead of searching a homolog model, we can simply get an AlphaFold model. So let's do that. Let's do molecular replacement with an AlphaFold model. So this is based on a tutorial data from Randy Reed, who is the developer of the Phaser software, which is used for molecular replacement. So the protein in question is called POMGNT2. And here you can see what it stands for, already very protein O-linked mannose, and so on and so on. And so the first AlphaFold database was trained on the protein data bank, so trained on all those models that are available or were available in the PDB in February this year. And at this time, there were no homologs of POMGNT2. And so that means that models built with this database had no templates. So this is an example of molecular replacement for a case where there are no templates for a particular structure. So meanwhile, however, the structure of this protein was solved. And so now let's do as if the structure is still unknown and we only have the data. So we can get the data for this model. It's 7E9J. That's the code you can use to retrieve a structure from the PDB. And we can also get the AlphaFold model for this protein. And again, this was determined without the template. And before we move on, I want to ask the participants one more question in order to interpret the results. So here I have two maps that represent or may represent a protein. And in your opinion, which map is better? The map on the left or the map on the right? And then also I see already some people put some answers in the chat and put also your reasoning. So the map on the left is better because, or the map on the right is better because. So I give you a couple of minutes. So we already have some answers. Yeah, I don't know actually about the threshold. I think it's a similar one, but it doesn't really matter that much. Okay, so we have, I think most people would say the right map on the right is better. And I agree. And the reason is that the density looks like protein. So here you can almost build manually some amino acids into the density. We have connected density. Several people mentioned that, connectivity. The map on the left here, there are many, let's say, holes, right? So, and if I increase the contour, then maybe some density will get more connected, but then I will also get more noise. And then there will be one more item, and that's a flat solvent region. And I think that was also mentioned somewhere. that we have that the solvent region is less noise. So all these are properties of a good map. So let's move on to our tutorial. So here is the AlphaFold model of our target protein. This is how it looks like. And let's just do brute force molecular replacement. So we try molecular replacement with the alpha model as is. We just take this model and put it into the program and see what happens. So this is what will come out of it. These are some scores. So we have an LNG score, which measures how much better the data can be predicted with the model than with a random distribution of the same atoms. So if this number is high, that's good. And then we have here another score. TFZ stands for translation function z-score. And if this is high, it's also considered good. So just by looking at these numbers, that's probably not too bad. But let's have a closer look at the model and the density that we got from here. So here, again, this is the predicted structure. And here we can see that there are three domains, right? We have this helix here, we have this bigger domain in the middle, and then we have the smaller domain on the left. And so here I show you some close-up view of this domain on the left. And again, I want you to look at this and put in the chat, do you think this is a model? Is this a good model? Or does this model explain this density? Would you say molecular replacement worked well here? So these lines here, if you're not familiar to this, represents the main chain. So it's the C alpha trace. So it shows you the lines between the C alpha atoms. So is this aligned? Well, it's just comes out of molecular replacement. So there's not really, I'd say, an alignment. Okay. A little bit more time to type. I think we have a clear consensus though. Okay, so one answer, for example, was the lines don't seem to match the density peaks, right? So for example, here we have, okay, here it's kind of in density, but here it's just traversing in these blobs, and there doesn't seem to be any density in between. So it looks like we didn't really catch the orientation of this domain here. And so, well, this structure has been determined, so we know the answer. So let's just superpose this to the structure that has been determined, and that's here. And oops. So if I go back and forth, you can see the deposited model that looks a little bit better, and than what we found from our molecular replacement. So it looks like the whole domain is hinged towards the upwards. So as a conclusion, the small domain was not well placed. So we did something wrong in our, or we did something not so optimal in our molecular replacement approach. So let's look a little bit closer at the result from the AlphaFold. So what these supply is the so-called predicted alignment error plot. This is a plot we can see here on the left. And so this predicted alignment error, this is low for residue pairs if the AlphaFold model predicts well-defined relative positions. So let's say if we here between 0 and what is this, maybe 30, well, we have this dark green color. That means the expected position error is low. So everything here between 0 and 30, here the relative positions are considered good. However, everything that is further away is bad. So what I tell you, you cannot necessarily know, but these first residues, that's actually this helix here. That means this long helix, this is considered, well, this is considered good. This forms a helix, but we don't know how it aligns with respect to these other two domains. And then we have this big blob here, and this represents this domain in the middle. And then we have this area here, this represents this domain here. So these domains are considered each in separation quite well, but then the relative orientation is unclear. So what we have to do for our molecular replacement is that we break it up into different domains. And then actually this N-terminal region is most likely a signal peptide. So it's not present in the mature protein. So we just don't use this N-terminal region. So we just look for domain number 2 and domain number 1. And we can do that in the phaser software separately. So we can supply models for the first domain, for the second domain, and then it will rearrange them, translate them, and rotate them each individually. And so we run it again, and what we get then, we get much better values. So now we have an LRG more than 4,500, and the TFZ is 35. I think before it was 725 or something. So the numbers look better. But again, let's look at the map, and here we have this time the density explains well how the domain has been placed. And if we superpose this to the deposited model, I don't remember, I think the red one is the deposited, no, the green one is the deposited model, the red one is after molecular replacement, and they're superposed quite well. So this, I hope this example shows you how AlphaFold models can be used for molecular replacement. And that's all I wanted to show you today in this presentation. And if you have any questions, I'm happy to answer them. And while you think about questions, I showed you the acknowledgement slide. So I told you already Phenix is developed by 5 groups, but of course there are many more people involved in the general Phenix project. So thank you for your attention.